Hello everyone. So this is going to be a video about confidence intervals and how to work through confidence intervals, how to do the problems around them, and how to apply them in specifically to your Stats 202 class. So, and again, if you're not from Stats 202, this will probably still be relevant even if you're doing confidence intervals in some other class. So yeah, we're going to work on confidence intervals. So I have a number of problems here that I've set out. For those of you in the stats class, this is in learning outcome 4, learning steps, just double checking, 2 and 3. Okay, so we're going to figure out how to construct a confidence interval. If you want to see the theory around it, this is not the place. We have, for the Stats 202, we have our manual. You can look at that and see the theory behind it. But so for today, I'm just going to walk you through how to do these problems so that hopefully this will help you out on your assignments. So the first one here, we're being asked to determine a 95% confidence interval for mu corresponding to a sample size of n equals 1000 with a sample mean of 35 and a standard deviation of s equals 4. So this is not a real world problem, but it'll sort of help you set up a problem if you wanted to, like the question I have from example 5 in the textbook below, this is a good example of sort of a real world problem that might be faced with constructing a confidence interval, and number 1 shows you sort of the template for doing that. Now if you look at the formula for confidence interval, you're essentially constructing a net around the sample mean, but each of these things has a corresponding quantity in the question. So you'll notice that x bar is right here, s is right here, and n is here. Now the last thing you notice is this z with alpha over 2. So there's a couple questions that come to mind. Well, first of all, which one of these confidence interval formulas should I use? As you've learned in your manual, this formula gets used if n is greater than or equal to 30. So if the number of data points is bigger than or equal to 30, then you use this formula. And this uses a standard normal distribution as opposed to its student t distribution. For this one, this is if n happens to be less than 30. You use this one, and you're using this little t quantity here. The t replaces the z, and that means you're using a different table. I have my formula sheet out, so instead of using this table, which is the standard normal z distribution, you're going to use this one, which is the t distribution. Okay, and then lastly, there's this one, and you use this one when you're dealing with a population proportion as opposed to a population mean. And we'll get into that as well in the last question that I want to do. Okay, so this first one, n equals 1000. So n equals 1000. So this is technically a large sample size. And that's the distinction, right? It's a large sample size. Specifically, it means that its n is greater than or equal to 30. Okay. The next question, though, is that how do I pick this z? And as you've seen in the textbook, or not the textbook, but the manual rather, the way you pick this is based on this alpha value. So the alpha value is always decided based on the confidence level. And when you get to hypothesis testing, this is going to be true as well. The alpha is always based on your confidence interval. So 95%, maybe I should use a blue pen just so that this looks a little bit cleaner. 95% is how confident you want to be. And this corresponds in decimal value to 0.95. So alpha, this is your error. That's what that term's called. It's called an error term. And because of that, this is picked based on, well, alpha is actually just equal to 1 minus your confidence. So 1 minus 0.95. And remember, I'm not subtracting off the percentage because really all percentages are just decimals. So 1 minus 0.95, this is going to be equal to 0.5. So then when you look here on the confidence interval chart and it says z of alpha over 2, well, they take alpha divided by 2 because when you're dealing with a confidence interval, it's a two-tailed thing, right? When you're trying to guess things, when you're making your confidence interval, and you don't have to draw things out. I'm just doing this to illustrate, this region in here is supposed to be 95%. So that means these two regions out here, these are your alphas. This total is alpha, so then each of them individually is alpha over 2. This same sort of technique gets used in hypothesis testing. This same idea and the same value, and what alpha is also used in hypothesis testing. And we'll get into that once we get into hypothesis testing, but for now, we'll just deal with it this way. So alpha over 2, this is just 0.5 divided by 2, 0.5 divided by 2, which is going to be 0.25. And then the confidence interval itself is pretty straightforward. It's just a matter of, well, our z of alpha over 2, this is literally just the value you'd get if you look on the z chart corresponding to that alpha. So if your alpha over 2 is 0.25, or 0.25, yeah, this is going to mean that right? So if I'm looking at my standard normal distribution chart, and this part right here is 0.25. Pardon me, that's I did that the wrong way. This should be 0.05, and this should be equal to 0.025. Okay, same difference. Well, that's my mistake. So if this little region in here is 0.025, that means that this region in here has to be 0.4975, right? So what that means is I'm going to have to find this on the chart and give me my z value back. So 0.4975, where is it going to live here? 0.4975, 2.81. So this Z alpha is equal to 2.81. And just to show you again, I found 0.4975 right down here. And then there was a 2.8 up here and a 1 up here. So 2.81 is my Z alpha value. So then when I construct the confidence interval, I use that formula that I had on the chart over here, this one right here, and I'm just going to put it on over here. So I have CI equals to X bar plus or minus. So we're going to take plus this and minus this and look at that. Z alpha over 2, S over the square root of N. So if I plug in the values, CI equals, well, my X bar is 35, plus or minus Z, which is 2.81. S is 4, so 4 can go on top, over the square root of 1,000. Now, in the end, I want to have an interval, and we're going to write it this way in little brackets and put a little comma in between. Down here, this is going to be, and maybe I'll write it down here. This is going to be X bar minus Z alpha over 2, S over the square root of N. And then up here is going to be X bar plus Z alpha over 2, S over the square root of N. When you're computing this, it's easier to compute if you just compute this whole expression all together and then just add it and subtract it. So let me get my calculator out and figure out what just this little bit in here is. So we have 2.81 times 4, okay, and then divided by 1,000, and I'm just going to take the square root, equals. So I'm getting that this is 0.355. I'll just use a couple decimal places there. Okay, so we have 35 plus 0.355, and I get on the top 35.355, and then on the bottom, we have 35 minus 0.355, and I get 34.645. So what that really tells us is that we are 95% confident that the true mean mu lies within this range right here between 34.645 and 35.355. And obviously that makes a lot more sense when you look at a problem like this. That's a real world problem, the one I'm going to look at next. And we're able to write out a sentence following that. But for one like this, we don't really need to add any sort of sentence. But that's the idea, is that we're 95% confident that our true mean, mu, the one we're trying to estimate, lies between these two numbers. Okay, so example number 5. It's the same sort of thing, but we have to figure out we have to use the numbers that we're given here to figure each of these out. Okay? So let's write out what we know. Right here we know, so let's look at this. So a group of patients were asked to rate their overall satisfaction with the physician who examined them on a scale from 1, of very poor, to 5. Suppose a random sample of 8 questionnaires were sampled for the physician, Dr. Jackal. Construct and interpret a 90% confidence interval for the following statistics. X bar equals 2.3 and S equals 1.25. So what it's saying here is that it wants you to figure out a confidence interval based on the sampled, like the average, the X bar sample was 2.3. They gave them an average rating of 2.3. But over those 8 questionnaires, the average rating would vary by about 1.25 on each of the individual questionnaires. So here we know that 8 questionnaires were sampled. We have a confidence of 90% and X bar and S. So remember, whichever one we look at, whether it's n is greater than or equal to 30 or n is less than 30, we still need our S, we still need our square root of n, we still need our X bar. But first of all, why don't we just figure out which one of these we need? Well, there was 8 questionnaires that were sampled. So it seems like that's going to be what our sample is. N equals 8, and this happens to be less than 30. So this is going to be a small sample. So what that means is we're going to use a t-distribution. Okay, so that means we're going to use this formula right here. And we just have to have all the other values available to us, right? So we know what S is, we know what N is, we know what X is. We just need to find that T alpha over 2. So alpha here is equal to 1 minus 0.9 because our confidence is supposed to be 90%. So our error should be 1 minus that. So 0.1. So that means alpha over 2 happens to be equal to 0.05 because if I take 0.1 and I divide by 2, I get 0.05. So we're not going to look at this one now. Now we have a new chart, but this one's incredibly easy to work with because we don't ever really use this to compute areas. I mean, we do use them to compute areas, but we don't use it as often in the way that we use the standard normal distribution in the last section. For this one, it's mostly just used for your hypothesis tests and for your confidence intervals. So it's actually incredibly well established for that, or it's well constructed to be able to work with confidence intervals and hypothesis testing. So now you'll notice on the column on the left here, there's degrees of freedom, and then you have your alpha value here. So this makes it really nice. All confidence interval stuff is actually 2 tails. The 1 tail is more, you see how it says 1 tail here, it says 2 tails here. That's more for your hypothesis testing. But confidence intervals are always under 2 tails. So if you look here, this alpha is 0.1. This means that we're actually going to, we didn't even really need to divide this out. We needed to divide it out for the Z value, but we don't really need to do it for the T value. I did it just to be consistent, but we don't because we can actually just look right here. 0.1, and we know we're in this column right here. Now, it also has its degrees of freedom. And the degrees of freedom, this is actually true. Anytime they talk about degrees of freedom in a basic statistics class, this almost always, except for in a couple distributions, almost always is n minus 1. Well, n is equal to 8, so the degrees of freedom should be equal to 7. So now what we have to do, well, you see that? I put 7 right there. Now what we need to do is find 7 as our degrees of freedom. and we need to say, well, the confidence interval is a two-tailed test, and our alpha was 0.1. So 7 and 0.1, we look on the chart, brings us over to here. I get 1.895. So this is saying to me that T alpha over 2 is equal to 1.895. So then when I do the confidence interval formula, CI equals 2.3, because, well, actually let's write the formula out again just to be pedantic. X plus or minus T alpha over 2. S, where's my S? 1.2, S over the square root of n. And now we plug all the values in. X bar is 2.3 plus or minus T alpha over 2, which is 1.895. S on top, which is 1.25. And on the bottom, the square root of n equals 8. Okay, so now we figure this out. This is 2.3 plus or minus, I'm going to just compute this little part in here. And it's, you might not be comfortable with fraction multiplication, but you can multiply this by the top and divide by the bottom. So 1.895 times 1.25 divided by 8, and I hit the square root button and I get 0.837. Sometimes your calculator might not do things this easily. It works okay for my calculator, but just make sure you're doing things the right way. It might even be easier to figure out this fraction first and then multiply it, just because sometimes calculators can do things in a really funny way. But whatever the case is, this is 2.3 plus 0.837. So then when I make the little, when I make my brackets, this is just saying interval, by the way. If you remember from high school math class, you write ranges out as intervals. So I'm going to say 2.3 plus 0.837 is going to give me 3.137, and 2.3 minus 0.837, and I get 1.463. So it does ask us, so that's the final interval. This is a score of 1.463, and this is a score of 3.137. So what this is saying is and it's asking us to interpret this. What this is saying is, so this was supposed to be a test of people's satisfaction of this doctor. Now, this is saying that the true satisfaction, so you only sampled 8 people, so you don't know if everybody is going to rank them, or what the true average ranking they're going to get is. You just know that those 8 people gave them a ranking of 2.3 on average. But you need to try to guesstimate, well, not guesstimate, but you want to try to estimate the actual ranking that the average person would give them in the wider world. So what this confidence interval says is that there is a 90%, how can I word this here? So there is a 90% chance that the true average rating of Dr. Jackal is between 1.463 and 3.137. Or in other words, we could say that the true average rating, or the population mean, of Dr. Jackal is between, we have 90% confidence that the true average rating of Dr. Jackal is between 1.463 and 3.137. Okay? All right. We'll do 2 more of these, and I'll try to go through them relatively quickly for you. And in the description box, I'm going to try to put links to each of these individual problems for you. So, okay, so next up, we want to determine a 99% confidence interval for mu corresponding to a sample size of n is equal to 25, x bar is equal to 80.5, and a standard deviation of 15.9. We already know mostly how to do this from the last problem, but we'll go through this one again because I want to get you some experience using the t-distribution. So n equals 25. Now this happens to be less than 30, so this is a small sample. And this means we have to use the t distribution. Okay, and this is a 99% confidence, so this means that our alpha is equal to 1 minus 0.99, which is equal to 0.01. This is so our degrees of freedom, I'll just put df here, is equal to n minus 1, like in the last problem. And this is going to be 24 because n is 25, so n minus 1, you take away 1 from that, you get 24. So we can look on our chart now. Alpha is 0.1, so, and it's a two-tailed test because, of course, this is a confidence interval. I'll just put a little CI here. 0.01 happens to be right here, so we know we're in this column. And the degrees of freedom, n equals 24. 24 is right down here, so this is the number I'm looking for, 2.797. So T alpha over 2 is equal to 2.797. So my confidence interval, I'm going to make it a little bit bigger this time just because it's getting kind of messy there, and I have lots of space. So this is T alpha over 2, S over the square root of n. Okay. And from here, I'm going to plug my numbers in. X bar is equal to 80.5 plus or minus T alpha over 2, which is 2.797. And if you're wondering why the alpha over 2 is still here, it's just to say that it is a two-tailed distribution here. So we have S. It's just acknowledging it more than anything. I know it mechanically you can just look it up on this table. It says two tails, no problem, but it's just sort of acknowledging that. S is 15.9 over the square root of n. N is equal to 25. What do we get here? So we have, and remember I like to compute this first. Hope we don't run out of room. We have 80.5 plus or minus 2.797 times 15.9 divided by 8. So I get 8.894, and 3 decimal places is just fine. So when I write this out, I have 80.5 minus, so I'm just going to put my little brackets in there, 80.5 minus 8.894. I get 71.606, and then finally add it the other way now, 8.894 plus 80.5, and I get 89.394. That's my confidence interval right down here. So again, we have a 99% confidence that the true mean mu lies within 71.606 and 89.394. Okay, the last one, this one's a population proportion. And the way we kind of understand this is because you're given some sample of, like, say 60 people, and there's some number of respondents, or some proportion of people out of that have the property that they reported. So let's read through this. Sorry, I'm jumping ahead. A random sample of 60 people are questioned about their average speed while driving on Highway 11 between Regina and Saskatoon. 36 of those people reported that their typical average speed is over 120 kilometers an hour. Sounds likely. Now, determine a 95% confidence interval for the proportion of drivers typically driving faster than 120 kilometers per hour on Highway 11. Now, you'll notice that. So what you should notice here is we take a sample, but then out of that sample, you have some number of those people with the property you're looking to test. Well, you're looking to test the proportion of drivers typically driving faster than 120 kilometers per hour. Well, 36 of the 60 said that their typical average speed was 120 kilometers per hour. And this proportion should be a huge keyword that they're looking for, proportion. And this is the one you're going to want to have to use. Okay, so the first thing you need, let's just look at the values here. You have n, and we already know what n is. N equals 60 in this case, right? There's n right there. We know what alpha is, of course. It is a 95% confidence interval, so alpha equals 1 minus 0.95, which is 0.05. anytime you're doing a proportion test, you have to do the Z test. So we can figure out Z alpha over 2 because, of course, alpha over 2 is equal to 0.025. Okay. You know what? I think I did that first problem incorrectly. I think I did. So I'll have to go back and make a correction on that. It's not hugely important because we did the other stuff right, but I actually realized the way that I did this, I believe, or no, I think that's right. No, never mind. Or no, that's not right. That's not right. Because this should be 0.475 is what this should be. Yeah, too bad. So just make note of that. I'll just point that out. And but the method is correct. It's just that this Z value is incorrect because of I just did these numbers in my head, and sometimes that thing can be a little unreliable. Whatever the case is, let's go through this. So Z alpha over 2, this is equal to, well, alpha over 2 is this, so that means that because this is a Z value, I have to kind of construct this and work backwards. So put this up. This is my alpha over 2, 0.025. So it's saying that this region in here is 0.475. Okay? And if we look on the chart here, one of the lovely things about these hypothesis tests, this isn't hypothesis testing, but the alpha comes up in hypothesis testing. But hypothesis testing, confidence intervals, is that we've been teaching it for so long that it's sort of, we've built things in to help ourselves out with it. So we're looking for 475. Now, where's 475? Oh, this isn't one where it's built in. Yes, it's right here. It's right here. 0.475. This is 1.9 and the 6 up here. So this is equal to 1.96. Okay. So 1.96, we have, 1.96 is the Z value. Now we need to know what P hat is. So if you look at these, and you should know this from reading the textbook as well, but if you look at this, we need to find this P hat value and the Q hat value. Well, fortunately enough, Q in a proportion question is always equal to 1 minus P. So Q hat is 1 minus P hat. So if you know P hat, you know Q hat. But P hat, this is equal to the number of people who reported their typical average speed over 120 kilometers per hour, because this is kind of like a sample proportion. Well, that's what it is. It's the sample proportion of the thing you're trying to test. And so you sample those 36 respondents, and you know that the total sample was, that you sample the 60 people, and you know that 36 responded that their average speed was over 120. So that's what we're doing over here. 36 goes here, divided by 60. So we have 36 divided by 60. We get 0.6. And then if this is just 1 minus P, this is equal to 1 minus 0.6, which is equal to 0.4. And now we just use the formula, just like before. CI equals P hat plus or minus Z alpha over 2, and then a square root over top of P hat times Q hat divided by N. So this is P hat, which is 0.6, plus or minus Z, which is 1.96, times the square root of P hat, which is 0.6, times Q hat, which is 0.4, as we figured out, divided by N, which is 60. Okay, so let's just figure this out. 0.6 times 0.4. I'm doing this stuff under the square root first so that I can square root it and make everything nice. I press the square root button and then times by 1.96. What do I get? I get 0.6 plus or minus 0.124. Okay, so when I construct that interval, I say 0.6 minus 0.124. This gives me 0.476, and then we have 0.6 plus 0.124, and I get 0.724. Okay, so what that's saying is that we have what is our confidence level? 95%. 95% confidence that the true average proportion of drivers going faster than 120 kilometers per hour is between 0.476 or 47% and 0.724, 72.4%. So the proportion of drivers, the average should be, well, we have 95% confidence that it's between 47.6% of drivers on Highway 11 and 72.4% of drivers on Highway 11. Okay, I hope that helps. Again, I made that little mistake over here. You know what, maybe what we'll do is, because I did make that little bit of a mistake, let's just go back and take a look at that again. And I'll just go walk through it and just make sure I get the right numbers, okay? So pardon me, I'm just going to flip the page quickly. It won't take very long to go through. I just want to make sure we're doing it right, so that you know what I'm doing. So again, here, n was equal to 1,000. Okay, alpha was equal to 1 minus 0.95, which was equal to 0.05. Alpha over 2 was then equal to 0.025. And since we're using z here, because it's n, this is large sample, so you use standard normal. So we draw our little graph to help us figure out where that z's living. We know that this alpha over 2 is 0.25, so this part in here must be 0.475. And then we look on that chart, and I mean, it's the same as the last question we did, but we look on the chart anyway, just to make sure we're following the process the right way. 0.475, that's 1.9 and a 6. 0.96, so Z alpha over 2 is equal to 1.96. So then CI is equal to, well, we knew that X bar was equal to 35 and S was equal to 4. So this was X bar plus or minus Z alpha over 2, S over the square root of N. Or in other words, just writing things out a little bigger, 35 plus or minus 1.96, I'll just put that in brackets, times 4 divided by the square root of 1,000. Or in other words, 35 plus or minus, going to get out the calculator, 4 divided by 1,000 square root times, oh shoot, that's not right, 1.96 times 4 divided by 1,000 square root equals 0.24, actually about 0.25. Just double check that here. Okay, everything works out. So it's about 0.25 when you round it. So this is equal to 35, well, I'll make my little brackets here, 34.75, and on the top end, 35.25. Okay, so in other words, we have a 95% confidence, or we have 95% confidence that the true mean, for whatever problem this is based around, is between 34.75 and 35.25. That's it for confidence intervals. I will be soon uploading the first part of doing hypothesis testing so that you'll be able to do assignment number 4. Thank you. Have a nice day.